Electronegativity of nitrogen is 3.0 and electronegativity of oxygen in alcohols is 3.5. When the molecular mass will gradually increase, we know that boiling point of that compound will also gradually increase. This basic strength of methylamine depends on the extent of hydration of methylammonium ions which are formed by the protonation of amines. The products obtained by acylation reaction are known as N-substituted amides. It is a reversible reaction. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Now, I am going to start session 3 from the chapter Organic Compounds containing nitrogen. In the previous session, we have discussed about preparation of amines by reduction of nitro compounds, ammonolysis of alkyl halides, reduction of nitriles, reduction of amides, Gabriel synthesis, Hoffman's bromamide reaction. In these kinds of reaction, how preparation of amines could be explained. This is about what we have discussed in the previous session. In current session, we will discuss about physical and chemical properties of amines. First, we will see the physical properties of amines. The lower aliphatic amines are gases with fishy smell. Lower means C1, C2, C3 like that. Lower members of aliphatic amines are gases with fishy smell, which is a pungent smell. Primary amines with 3 or more carbon atoms are liquid and higher members are solids. More than carbon, 3 amines will have liquid in nature, More than that will be solids in nature. Usually C1, C2, C3 are gaseous in nature. This is about the states of matter of amines. Next, we will see the solubility. Lower aliphatic amines are water soluble because they can form hydrogen bonds with water molecules. Lower aliphatic members or amines like C1, C2, C3 will form hydrogen bond with waters. That's why they are water soluble in nature. However, the solubility decreases with increase in hydrophobic alkyl group. When the hydrophobic alkyl group is keep on increasing, then the solubility of members of amines in the water will get decreases. Only the lower aliphatic amines will get dissolved in water. Aromatic amines are insoluble in water but soluble in ether, alcohols and benzene. Aromatic amines are higher member of amines and they are insoluble in water because they does not form hydrogen bond with water, and also it will solvents like ether, alcohol and benzene. By considering the electronegativity of nitrogen of amine and oxygen of alcohol, we can predict the pattern of solubility of amines and alcohols in water. Here we are comparing with solubility of alcohols and solubility of amines with respect to water by using electronegativity. Okay, electronegativity of nitrogen is 3.0 and electronegativity of oxygen in alcohols is 3.5. By comparing these electronegativity values, we can predict that alcohols are more polar than amines and form stronger intermolecular hydrogen bonds than amines due to this electronegativity difference. Alcohols are having more electronegativity value and they will form strong intermolecular hydrogen bond with water rather than amines, and alcohols are more polar in nature. Therefore, among butanol and butanamine, butanol is more soluble in water. Due to this electronegativity difference, we can predict that alcohols are more polar and they are having strong intermolecular hydrogen bond formation with water. That's why it will only more soluble in water comparative to amines. Next, boiling point. All amines except the tertiary amines are capable of forming intermolecular hydrogen bonds due to the presence of polar NH bond. All amines except tertiary amines will form polar nitrogen-hydrogen bonds. So, they will form hydrogen bonding. That's why the boiling points rise gradually with increase of molecular mass. When the molecular mass will gradually increase, we know that boiling point of that compound will also gradually increase. Therefore, boiling point is less in tertiary amines than primary and secondary amines. Hence, the order of boiling point is isomeric amines. Therefore, due to the NH bonds and due to gradual increase of molecular masses with respect to boiling point, here we can tell tertiary amines having less boiling point comparative to primary and secondary. The order of boiling point of isomeric amines is primary amine having greatest boiling point range, next secondary, next tertiary. Okay, this will be the least boiling point range. Intermolecular hydrogen bonding in primary amine. How intermolecular hydrogen bonding will be present in primary amine? Through NH bonds, means hydrogen and nitrogen bonds. This is bonding. Okay, that's why it is strong due to this bonds. Next, basic character of amines. Like ammonia, amines are bases and react with mineral acids to form ammonium salts. NH3, which is ammonia, we can tell that amines also basic in nature, and that's why it will react with mineral acids to form ammonium salts, NH4 plus salts. This reaction shows that amines are basic in nature due to the presence of unshared pair of electrons on nitrogen atom. Okay, due to the presence of this unshared pair of electrons above nitrogen, they are electron rich in nature. Usually electron rich means nucleophiles. Nucleophiles will be considered as basic in nature. That's why in amine, nitrogen has having unshared pair of electron, and also this amine will react with mineral acids to form ammonium salts. Those are all those results can only show that amines are basic in nature. Based on pKb values, we can decide the basic strength of the amines. Lesser pKb value, stronger is the basic strength. And also we have one theoretical proof that pKb value is less, then the basic strength will be more. pKb is inversely proportional to the basic strength of any solution. See here, when amine is treated with hydrogen halide, it will form salt. When aromatic amine treated with mineral acid like hydrogen chloride, it will form anilinium chloride, which is a salt. Okay. Here also, by showing this example reaction also, we can tell basic character of amines. Variation of basic strength of amines in gas phase medium. Among primary, secondary and tertiary aliphatic amines, the electron releasing effect is maximum in tertiary amines and minimum in primary amines. Okay. Among primary, secondary and tertiary aliphatic amines, the electron releasing effect is maximum, means electron donating effect is maximum in tertiary amines and minimum in primary amines. Therefore, the basic strength is expected to increase from primary amine to tertiary amine. Okay. The basic strength is expected from primary amine to tertiary amine. The observed basic strength of methylamine, dimethylamine and trimethylamine has been found to follow the expected order in gaseous phase or in non-aqueous solvents like chlorobenzene. Here tertiary amine, secondary amine and primary amine, okay, in the gaseous phase. For example, trimethylamine, dimethylamine and methylamine. The basic strength of amine depends on, usually the basic strength will depends on some of the characters. With respect to amine, they are dependent on plus I effect or positive inductive effect, extent of hydration by hydrogen bonding, steric effect. First we will see the first effect, plus I effect. Electron donating inductive effect increases the positive strength of amines by increasing the electron density on nitrogen atom. Okay, positive means we know that they will donate some of the electrons. So, plus I effect means electron donating inductive effect is increased with respect to basic strength of amines by increasing the electrons on nitrogen atom. More the methyl groups attached to the nitrogen atom, more is the plus I effect, and hence the basic strength of methyl amines. Thus, based on plus I effect, the relative strength of these amines will be tertiary, next secondary and primary. Here in tertiary, amines will be here one, here R will be more, correct? So, whatever the nitrogen are having the electron density, it will be donated to the methyl groups, whatever they are surrounding to the nitrogen. So the electron donating capacity will be more and electron density will be more on nitrogen. So basic character will also increase. That's why tertiary is greatest, then secondary, next primary. This is about plus I effect. Next, hydration effect. Basic strengths of methyl amines depend on the extent of hydration of methyl ammonium ions which are formed by the protonation of amines. This basic strengths of methyl amine depends on the extent of hydration of methyl ammonium ions which are formed by the protonation of amines. That hydration will formed by the protonation of amines. The extent of hydration of the cations in the order first primary, later secondary and tertiary. In the primary, you can see here protonation. The extent of hydration will be both the side. Later with alkyl and hydrogen, here only one side. Okay, here hydration will be 3 sides. Here hydration will only 2 sides. Here hydration only 1 side. The extent of hydration is going to lesser from primary to tertiary due to the protonation effect. Next, steric effect. The basic strength of amines depends on the ease with which protonation of amines takes place. Where protonation of amines will take place, their basic strength of amines will be greater. The presence of bulky alkyl groups hinder the protonation. This hindrance is called steric hindrance. Due to the bulky nature present surrounding the nitrogen, the protonation of amines will not take place very easily. So, more are the alkyl groups present in the amines, more is the steric hindrance. Whenever more methyl groups or alkyl groups are present surrounding the nitrogen, there is more steric hindrance. Therefore, basic strength of methyl amines are in the order primary, next secondary, next tertiary. Because tertiary only having bulky groups more, that's why it is in least position. In the primary amine, there doesn't have that much bulky groups, so it is having more basic strength with respect to steric effect. Alkyl amines are stronger bases than ammonia. How alkyl amines are stronger bases than ammonia, we'll see. This is due to electron releasing inductive effect of alkyl groups. We have seen what is electron releasing inductive effect, which can donate electrons easily and it is present towards alkyl groups, that's why it is strong. Also, alkyl groups by their electron releasing effect increases electron density on nitrogen and hence make the lone pair of nitrogen more easily available for sharing with proton. We know that based on electron releasing inductive effect, electron density or electron rich on nitrogen atom, so it will make easily to availability of lone pair to make sharing with proton. Moreover, electron releasing effect of alkyl groups stabilizes the alkyl ammonium ion formed from amine due to dispersal of positive charge by plus I effect of the alkyl group. For example, methyl amine is more basic than ammonia. This is because methyl group is electron donating group and increases the electron density on nitrogen atom. Okay, whatever the alkyl group is present towards the nitrogen is also electron donating group. So that's why on the nitrogen electron density will also get more. This makes the lone pair of electron on nitrogen more easily available for the sharing with proton of the acid. Already nitrogen is having lone pair, that methyl attached to the nitrogen will also do the electron donating to the nitrogen itself. So availability of the lone pair of electrons on nitrogen will be easy for the reaction with proton of acid. That's why alkyl amines are stronger bases than ammonia. Another example we'll see, aniline is less basic than ammonia. This is because phenyl group of aniline exerts minus I effect which withdraws the electrons due to its resonance. Alkyl halides are more because it doesn't have any resonance structure, but in aniline it has one ring structure. Wherever ring structure is present or phenyl group is present, it is withdrawing group, and wherever withdrawing group is there, there can exert minus I effect due to its resonance. This results in the lower availability of electrons on nitrogen for protonation. Due to the ring structure involved in resonance, it doesn't have the availability of electrons for the protonation of nitrogen. So this results in lower availability, and in aniline or other aryl amines, the NH2 group is attached directly to the benzene ring. It results in the unshared electron pair on nitrogen atom to be in conjugation with the benzene ring, and thus making unshared electron pair less available for protonation due to the following resonance structure. See here, for this benzene ring itself, nitrogen is attached, and that lone pair of electrons of nitrogen should be in conjugation of benzene, not for the availability of the further reaction with acid. So it will involve in resonance, and those lone pair will come to the benzene structure, and here resonance will start, and it will be turned to the nitrogen itself. Correct? You know how to write the resonance form of resonance structures of any of the molecule. Here, that's why aniline is less basic, which is having phenyl group comparative to ammonia. On other hand, anilium ion obtained by accepting a proton can have only two resonating structures. Anilium ion means it is NH3 plus, so it is having only two resonating structure, no other resonating structure are present. Greater the number of resonating structure, greater is the stability. Thus, aniline is more stable than anilinium ions. When resonating structures are, stability is more. When here in anilinium ion only two resonating structures means aniline is more stable or more having stable than aniline. Okay, and basic nature of aniline or other aromatic amines would be less than that of ammonia. Next, chemical properties of amines: acylation or acetylation. Okay, we have seen the physical properties. Now we are moving to the chemical properties of amines. In that acylation or acetylation, primary and secondary amines, both aliphatic and aromatic, react with acid chlorides, anhydrides and esters by nucleophilic substitution reaction. This reaction is known as acylation. The products obtained by acylation reaction are known as N-substituted amides. It is a reversible reaction. Here, primary or secondary amines can involve in the reaction, and it may be aliphatic or it may be aromatic, and it will react with acid chlorides, anhydrides and esters by nucleophilic substitution reaction. That reaction will be called acylation, and the products will be called it as N-substituted amides, and it is a reversible reaction. Primary amine react with acyl chloride in the presence of pyridine. It will form N-substituted amide. Example: acetyl chloride reacts with methyl amine in the presence of pyridine base to form N-methyl acetamide. Okay, methyl amine, this is amine with methyl, and acyl chloride in the presence of pyridine, which is a base, it will form N-methylene amide. Okay. At the end, amide only should form. Dimethyl amine reacts with acetyl chloride in the presence of pyridine base to form N-diethyl ethanamide. This is diethyl amine, react with acyl chloride in the presence of pyridine. It will form N-diethylene amide. Okay. Aniline reacts with acyl chloride, acetyl chloride in the presence of pyridine base to form N-phenyl ethanamide. This is a having phenyl ring structure. Aniline present with acetyl chloride form in the presence of pyridine. It will form N-phenyl ethanamide. Means aliphatic also you can expect, aromatic also you can expect. Next, carboxylamine reaction. When aliphatic and aromatic primary amines are heated with chloroform and ethanolic potassium hydroxide, carbylamines or isocyanates are formed. This reaction is known as carbylamine reaction or isocyanate test. This is used as a test for primary amines. These carbylamines have very unpleasant odors. Secondary and tertiary amines do not respond to this test. This reaction used test for the primary amines. When aliphatic and aromatic primary amines reacted with chloroform and ethanolic potassium hydroxide, carbylamines will form, and this reaction will only give the test for primary amines, and it is used to distinguish between primary, secondary and tertiary, but this test will not respond with secondary and tertiary amines. This is primary amine, chloroform with alcoholic or ethanolic potassium hydroxide. When heated, isocyanate or carbyl amines will form. Here methylamine react with chloroform and KOH. When heated, methyl isocyanate will form. Phenylamine react with chloroform and alcoholic KOH. Phenyl isocyanate will form. Reaction with nitrous acid. First with aliphatic primary amine. Aliphatic primary amines react with nitrous acid prepared in situ from sodium nitrite and a mineral acid such as HCl. How nitrous acid will prepared? From sodium nitrite and HCl to form unstable aliphatic diazonium salts which further produce alcohol and HCl with the evolution of N2 gas by hydrolysis. This is primary amine. This is nitrous acid. It will be formed from NaNO2 plus HCl. See here, in the presence of NaNO2 plus HCl, it will form aliphatic diazonium salts which is unstable and later it will hydrolyze to form alcohols. Example, methylamine reacts with nitrous acid to form methyl alcohol with evolution of nitrogen gas. Here and here nitrogen gas will be evoluted. With aromatic primary amine, we'll call it as diazotization. Azo means nitrogen, di means N. Aromatic primary amines react with nitrous acid at low temperatures to form diazonium salts. This reaction is called diazotization. They may ask like, what is diazotization? Explain with an example. So it is very much important. For example, on treatment with when aromatic phenyl amine is treated with sodium nitrate and HCl at 273 to 278 Kelvin, aniline produces benzene diazonium chloride with NaCl and H2O as byproduct. This is aniline treated with nitrous acid. It will form benzene diazonium chloride. This is diazonium chloride. This is benzene. Okay, it will form the byproducts of sodium chloride and water. This is very important reaction. Next reaction with benzene sulfonyl chlorides. Benzene sulfonyl chlorides, we'll call it as Hinsberg reagent, reacts with primary and secondary amines to form sulfonamides. In this reaction, the amines are allowed to react with Hinsberg's reagent, benzene sulfonyl chloride. The three types of amines react differently with Hinsberg's reagent. Therefore, they can be easily identified using Hinsberg's reagent. Primary amines react with benzene sulfonyl chloride to form N-alkyl benzene sulfonyl amide which is soluble in alkali. This is benzene sulfonyl chloride. They are reacting with primary and secondary amines. Here they have taken ethyl amine to form N-ethyl benzene sulfonamide which is soluble in alkali. Due to the presence of a strong electron withdrawing sulfonyl group in the sulfonamide, the hydrogen attached to nitrogen can be easily released as proton. So it is acidic and dissolves in alkali. How it will be dissolved in alkali? Here the hydrogen will be easily liberated out when it is dissolved, or it can easily give as proton. So it is dissolved in alkali because it will be considered as acid. Secondary amines react with Hinsberg's reagent to give a sulfonamide which is insoluble in alkali. This is benzene sulfonyl chloride. This is diethyl amine which is a secondary amine. Form N and diethyl benzene sulfonamide. It is insoluble in alkali. Only primary product which will form from primary amine will soluble in water. From secondary amine which product will form, that will insoluble in alkali. There is no hydrogen atom attached to the N atom. See here, there is no hydrogen atom in the sulfonamide. Therefore, it is not acidic and insoluble in alkali. On the other hand, tertiary amines do not react with Hinsberg's reagent. It will not react with tertiary amines. Primary amines which give the product will soluble in alkali because nitrogen with hydrogen is attached, it will be released as proton and it is considered as acid, so soluble in base. But the product which is from secondary amine will not attach it to hydrogen and it will not released as proton, so it will not dissolved in insoluble in alkali. And tertiary amines do not react with this Hinsberg reagent itself. Next, electrophilic aromatic substitution. Aryl amines are very reactive towards electrophilic aromatic substitution. This is because NH2, NHR2 and NR2 are very strong activating groups and are ortho para directing gives ortho and para substituted product. This is nitrobenzene, very much reactive towards electrophilic substitution reaction, and at the ortho and para position, the substituted products may expect. NH2, powerful activating group towards ortho and para director. Okay. Bromination. Aniline reacts with bromine water at room temperature to give a white precipitate of 2,4,6-tribromoaniline. Here aniline react with bromine in the presence of water. Here also 3 molecules of bromine is there. 2, 4, 6 tribromoaniline will be released with hydrogen bromide. Monosubstituted aniline derivative can be obtained by protecting amine group by substituting. Hydrolysis of substituted amide gives substituted amine. Here only monosubstituted will form N-phenyl ethanamide. Next, bromine will give 4-bromoaniline. That is amide, bromoamide will give most substituted aniline. Okay. Next, nitration. Direct nitration of aniline with nitric acid gives a complex mixture of mono, di or tri-nitro compounds and oxidation products. If direct nitration of aniline is carried in the presence of with a mixture of concentrated nitric acid and concentrated H2SO4, aniline gets protonated to form anilinium ion, which is meta-directing. Hence, nitration of aniline gives meta-derivative along with ortho and para. Here aniline in the nitrating mixture, that is concentrated nitric acid and concentrated sulfuric acid at 288 Kelvin, it will form ortho, meta and para, but ortho and para are very less mixture, but meta directing product will be in more. Monosubstituted aniline derivative can be obtained by protecting amine group by acetylation with acetyl chloride. Then carry out the desired substitution followed by hydrolysis of substituted amide to the substituted amine. Thus, nitration of aniline is carried out by first protecting amino group by acetylation reaction with acetyl anhydride. The nitration reaction can be controlled and the para-nitro derivative can be obtained as the major product. Here, monosubstituted aniline will form N-phenyl amide, and later when reacted with concentrated HNO3 and concentrated H2SO4, which is a mixture, it will form para-nitroacetanilide and para-nitroaniline. Okay, this is amide and this will also form aniline. Okay. Next, sulphonation. Aniline reacts with concentrated sulfuric acid to form anilinium hydrogen sulfate, which on heating with sulfuric acid at 453 to 473 Kelvin produces para-aminobenzene sulfonic acid, commonly known as sulfoanilic acid, as the major product. This aniline reacts with sulfuric acid, form anilinium hydrogen sulfate salt. Later, it will form sulfoanilic acid with zwitter ion. Here, they may ask in sulfonation which ion may form as in a MCQ pattern. So, zwitter ion will form. This is about the physical and chemical properties of amines. In the next session, we will discuss about diazonium salts, its preparation and chemical properties and physical properties. I hope you have understood completely whatever I have taught in this session. We will meet in the next session. Till then, thank you.